Probably my card is not the same as yours, since my time zone is in Taiwan, so like a 4 in the morning. Welcome to the second session. This is about the 3D designs of our chip. Let me introduce the first speaker. Dr. Ramini is a PhD student at the engineering department of the University of Colorado, Cary. His research includes modeling, simulation design of scale optical NoC chips. Please.
Thank you for my personal presentation. So, in this presentation, we are going to talk about power efficiency of wavelength-routed optical NoC topologies for global connectivity of 3D multicore processors. So this work has been supported by the University of Ferrari in Italy and also by the Photonica project. So, as you will know, for the first time, all photonics elements necessary to build an optical on-chip communication infrastructure, such as modulators, photodetectors, CMOS drivers, and receiver, are available for integration on a silicon chip. In fact, all these devices can be accommodated in the same environment. Typically, the target platform used for embedding chip-scale optical interconnect technology is represented by a 3D stacking system where processing, memory, and optical layers can be integrated in the same environment. So, moreover, thanks to the current roadmap, in fact, the current roadmap aiming at power efficiency below 1 milliwatt per gigabit per second per link, and also the throughput is at 1 terabit per second per link. So, one of the most famous optical network on chip presented in the recent literature is the space-routed optical NoCs, typically work proposed by Columbia University. So in this case, notice that they leverage a 3D stacking approach where we have a processing plane which is typically located at the bottom of such a structure. The electronic plane and the photonic plane instead are vertically stacked on the top of it. So here, if you want to reserve a path between a couple of source destinations, the following steps must be accomplished. We have path setup request, path acknowledgement, data transmission, at the end we have to turn down. And another transaction can be done. So unfortunately here, the optical path control is really expensive due to high NoC topology, path setup latency, and also contention. So in fact, this kind of mechanism is really inappropriate for cost and or latency constrained communications. Our work instead is really focused about wavelength-routed optical network on chip. This kind of optical network rely on the principle of wavelength selective routing. In fact, as you can see here, if the initiator I1 wants to communicate with 4 different targets, T1, T2, T3, and T4, this is possible by using 4 different wavelengths, the 1, 2, and 3, and 4 respectively. So notice that here, no time is spent in routing and arbitration functionality, and also this kind of network enable contention-free for connectivity without needing for any path setup, enter down, override. Certainly, this is an appealing property for processor memory network and a mix of criticality systems. So, however, although in literature there are a lot of works about this kind of optical networks, but unlike this, these works are strictly oriented on a theoretical study, thus overlooking physical implementation effects. Moreover, this kind of network suffer in terms of scalability. In fact, when increased number of communication actors, increased number of wavelengths you need, and then increased number of lasers, and also the optical network interfaces becomes really complex. In fact, increased number of modulators and receivers. So the key motivation of our work is that we need of a pathfinding. So if you look the recent state of the art about optical network on chip, we can find 3 important families. We have the silicon photonics families, where the key goal is to improve the quality metrics of modulators, receivers, switching elements, and so on. Moreover, there is another family all about on-chip communication architectures, where here the key goal is to combine silicon photonics devices and also higher order switching fabrics. But between these 2 different worlds, there is a gap. In fact, this gap is called phase transition problem from electron to optical NoCs. Moreover, the key issues here that are unexplored so far are physical design predictability, also physical deviation between logic and its physical implementation, actual placement constraints, and also utilization policies of either interconnects. So very far from here, there is another word, system interconnects, where in this case, there are a lot of research work where they are working about system level design around an optical interconnect. In fact, we have work proposed by Columbia University, we have a Charles, and also one work proposed by the University of Tehran, we have a hierarchical rings, and also Corona and Firefly. So in this specific case, the key features are scalability to 100 cores, cache coherency signal, and so on. So our work instead is here, because we would like to bridge the gap in the phase transition problem from electronic to optical NoCs. In fact, in our work, we would like to assess the deviation between logic scheme and its physical implementation under the effect of placement constraints, but targeting real-life systems. In fact, in our work, we would like to quantify the design predictability gap of wavelength-routed optical NoCs under the effect of placement and routing constraints in our system, our target system. In fact, there exists a physical gap between an appealing logic topology and the corresponding physical one in terms of insertion loss, delay, and power, and so on. Moreover, physical layer awareness is certainly a right way to quantify this deviation, but not just to identify if a specific topology is better than another one, or is more efficient than another one, but even more important, to identify its feasibility. In fact, when you place a route, an appealing logic topology into its physical implementation under the effect of placement and routing constraints, especially in those cases where the logic topology is characterized by unrealistic placement assumptions, the situation becomes unrecognizable. In fact, the first key effect is an increase of waveguide crossings in the real layout. As a consequence, the insertion loss and the laser power requirements may worsen so much that this appealing logic topology become overly expensive and in many cases unfeasible. So these effects are strictly design specific, and then I urge the choice for an experimental setting. In our case, we study processor memory communication in a 3D stacking approach. In fact, our target architecture is a 3-dimensional system, and it embeds an electronic layer which is located at the bottom of such a structure. Instead, we have an optical layer which is vertically stacked on the top of it. So we leverage TSV because they work like a backbone for uploading and downloading information, and they also bridge these two important layers. So in our work also we use an array of continuous wave lasers which are used to provide the optical power inside the optical layer. Moreover, thanks to the seamless scaling of the optical layer to the RAM chip communication, we leverage on optical fiber to connect memory controllers with chip DRAM DIMMs. As you can see, this scenario is certainly promising for cost-effective integration of heterogeneous technologies. More in details, our electronic layer consists of 64 cores, which are connected by using an electronic network on chip with a 2-dimensional mesh topology like this. In our work, we assume that cores are clusterized into 4 clusters, where each of them consists of 16 cores. Moreover, we assume that each cluster has a private access to the optical layer, which is vertically stacked on the top of it. Moreover, we assume that core size is 1 millimeter by 9 millimeter, and the die size is 8 millimeter by 8 millimeter. Notice that the aggregation factor in our work is represented by the number of cores inside each cluster. The optical layer instead consists of 4 gateways, which here are named hubs, H1, H2, and 3 and 4. And also it equips 4 memory controllers, M1, and 2, and 3, and 4, which are connected by using fiber ribbon with chip DRAM DIMMs. As I said before, we use an array of continuous wave lasers, where each of them is tuned on a precise wavelength, like the 1, 2, and 3, and so on. Notice that the same wavelengths can be shared by all initiators, and then hubs and memory controllers too. Our optical layer enables 3 kinds of communication scenarios. The first one is inter-cluster communication, and then communication among clusters. Moreover, we have processor memory communications, and then communication from a cluster to a memory controller, and vice versa. So, as I said before, placement constraints are certainly the key contribution to this work. The first placement constraint lies in the position of memory controllers. Memory controllers, in fact, are positioned pairwise at the opposite extreme of the optical layer, thus reflecting a common industrial practice. We think about Tyler 64. Instead, hubs are located along a square in the middle of each cluster. In our optical layer, we have to connect 8 initiators with 8 targets. And one possible way is to liberate wavelength-routed optical NoC to satisfy all communication requirements, inter-class, processor memory communication, and so on, in order to enable global connectivity. In fact, all the most relevant wavelength-routed optical NoCs logic schemes proposed in the research literature, such as lambda router, G-Bor, the crossbar, and the ring, were explored in our work with awareness of placement constraints, of physical constraints. Unfortunately, due to the lack of an automatic, suitable and good automatic placer route tool for optical NoCs, in our work we had to manually placer route the connectivity pattern of all topologies analyzed, thus using a full custom design solution. So this one is the first topology analyzed in our work. It is the 8x8 lambda router. As you can see, here we have 8 initiators that communicate with 8 targets by using 8 different wavelengths. Notice that in this case, the network utilized 8 stages of 4 and 3 ad-drop filters in alternative way. So notice also that this kind of network reflects the typical network used in electronic domain, the multi-stage network. But here, the interstage pattern is strictly related to the routing methodology characteristic of wavelength-routed optical NoCs. So unfortunately, notice that all initiators and targets are placed respectively at the leftmost and rightmost side of the network. This is certainly an assumption somewhat realistic. In fact, when you translate this logic scheme into its physical implementation under the effect of the placement-related constraints, the situation changes. In fact, the design guidelines used in our work for manual layout are the following. Firstly, we satisfy our placement constraints, and then position of hubs and memory controllers too. Secondly, we homogeneous spread all building blocks, all filters, in order to use as well as possible all the two-dimensional space. Notice that at every slice of the layer, we have at least 11 micro-resonators, where the total number is instead 56. Third, we place optical filters close to initiators, notice that the big one, and close to targets, the black one, and close to other PSCs, notice the blue one. Finally, we route optical wavegates in order to minimize, as well as possible, all crossing intersections. The second topology analyzed was the 8x8 G-Bor. Notice that here we have 7 wavelengths that are used to satisfy all global connectivity. This kind of network is built upon its basic cell, the 4x4 G-Bor. The 4x4 G-Bor is that cell. Consists of 4 wavegates which intersect each other. And notice that micro-resonators are placed pairwise at every intersection. Notice that to construct this network, 6 4x4 G-Bor cells are needed. Moreover, in this case, self-communication is forbidden. A specific features of this topology is that cores are positioned around a centralized open interconnector. Instead, this is the result when you translate the logic scheme into its physical implementation under the effect of placement constraints. Notice that placement constraints of the target system are certainly different from those of the logic scheme. And as a consequence, we have a circuitous and intricate layout that makes the logic scheme hardly recognizable. So in fact, there is an increase of wavelength crossings as an effect of the mapping on the two-dimensional surface. Moreover, another topology analyzed was the unoptimized crossbar, which here were referred by 8x8 folded crossbar. For reason of brevity, we explain its functionality by considering just 4 initiators and 4 targets. So if you look at the 4x4 original crossbar, notice that micro-resonators are placed at every intersection. And also, if the specific initiator sends optical message to all targets by using a given order. So if you change this order, like this, we obtain a 4x4 folded crossbar. Notice that we have a folding network. So at logic scheme level, this effect is certainly a wavelength length over length. But when you translate this logic scheme into its physical implementation by considering 8 initiators and 3 targets, if we talk about the 8x8 for the crossbar, the situation is better. In fact, this effect is not a drawback, but it is an advantage in the real layout. In fact, every initiator can drive an optical wavelength that enters in a ring-like topology, like this. This is an example of the path. Notice that the most important contribution in insertion loss is a crossing loss. Even here we have 7 distinct wavelengths which are needed to deliver all global connectivity. Here we compare all real layout across all topologies, and notice that this layout is certainly much more regular than that of those other topologies. And even here we have that micro-resonators are positioned close to communication targets, thus facilitating the wavelength ejection of optical signals. In this table, we compare this topology in terms of micro-resonators and the crossings in the critical path, considering the logic scheme and its physical implementation. Notice that the 8x8 lambda router counts for the maximum number of micro-resonators. Instead, for the crossbar, the minimum number. In the critical path insertion loss, the logic scheme, 8x8 lambda router counts for the minimum number of crossings, and for the crossbar, the maximum, 18. But when you translate the logic scheme into its physical implementation, surprising situation is opposite. In fact, the folded crossbar counts for the minimum number of micro-resonators, the crossing, sorry, and again it's 72 in the 8x8 form. This is means by the mapping on the two-dimensional surface. So similar to electronic network on chip, which the critical path is given by in terms of time, when we talk about optical network on chip, the critical path is in terms of insertion loss. In fact, this quality metric must be quantified to determine the laser power requirement that enables a predefined bit error rate at the photodiodes. In fact, this inequality must be absolutely satisfied. As you can see here, once the max insertion loss across all paths, IL max, is given, is obtained, and the detector sensitivity is known, it is possible to determine the lower limit of optical power to correctly detect the optical message at the receivers. Trivially, insertion loss is given by the sum of all losses parameters in a given path, such as DSCs, stray, band, and crossing wavelengths, all components to combine on a particular path. And also in our work, we assume that every crossing was optimized by using the standard elliptical table, like this. In our work, we rely on a Simulink simulation framework to assess insertion loss of all optical networks by modeling every single path for a given topology. Secondly, we calculate IL max for a specific topology across all paths of the same topology. Finally, we make the practical assumption that all laser sources of a given topology are sized based on this IL max. As you can see here, we compare the insertion loss across all topologies analyzed so far, contrasting logic scheme and its physical implementation. Notice that the G-board counts for 72 crossings in the real layout, instead 10 crossings in the logic scheme. In a similar fashion, the router reports 74 crossings in the real layout and 7 in the logic scheme. both topologies are crossing dominated. In fact, IL max is higher more than 6 times with respect to the corresponding logic scheme. Instead, at logic scheme level, as you can see here, crossbar is certainly worse because it's a crossbar. In fact, counts for the maximum hour insertion loss. But surprisingly, when you map this topology into its physical implementation, and this crossbar maps better our placement constraints, I mean, the situation is opposite. In fact, it counts for the lower number of insertion loss, 15 dB against 37 and 53 in A by A G-board and under router. So, and the critical path is not crossing dominated, but both waveguide and crossing dominated. We have also compared all topology in terms of power. Notice that when you talk about wavelength-routed optical NoCs, the total power is given by lasers power, modulators power, receivers power, and thermal tuning, the heating. As you can see here, G-board counts for is inefficient. In fact, achieves almost 17 watts. Even if lambda router has one laser more than G-board and for the crossbar. In the second position, we have the lambda router. In fact, it is almost 2.5 times lower than G-board. The most efficient solution right now is the folded crossbar. In fact, it consumes just 0.27 watts. So, as you can see, certainly G-board and lambda router are unfeasible, are inefficient, especially when you target global connectivity. More in details, we show the breakdown in terms of power. Notice that insertion loss is an important metric because it leads to higher insertion loss, leads to an increase of lasers and modulators powers. In fact, they become relevant and preponderant in the breakdown. In fact, notice that here, since G-board and lambda router are characterized by higher insertion loss, in the breakdown we have modulators power, laser powers are preponderant. Surprisingly, not surprising, so this is the key features of the crossbar. For the crossbar counts for the minimum number of insertion loss, and then the contribution of lasers and modulators is certainly lower, but is dominant the receiver power. So, since in our work we would like to find the best solution for our optical layer, we compare the 8x8 for the crossbar with a ring topology. So, as you well know, ring topology is the easiest solution. I mean, because it's characterized by higher simplicity, lower implementation cost, and so on. In fact, in our work, we designed an optical ring by using 7 wavelengths, as is in the crossbar. And notice that we use multiple waveguides by leveraging the spatial division multiplexing approach in order to satisfy all communication scenarios, processor memory communication, and intercluster tools. Notice that ring topology maps better our placement constraints, and also it works like a bus, which includes multiple waveguides. Here we have 7 waveguides to satisfy all communication scenarios, all global connectivity. But in the ring topology, there is a problem. In principle, in any ring topology, there are no crossing. But actually, they are localized at the initiator interfaces. In fact, when you have to connect the injection point to the furthest transmission side, here, we have the crossings. And these crossings works like obstacles that increase insertion loss and the total power. Instead, at the target interfaces, any crossing appears because the optical power is immediately collected by the photodetectors, and the optical power goes down by using TSV in the underlying electronic layer. So here we compare in terms of IL max and total power, ring topology and the folded crossbar. So as you can see in terms of insertion loss, 7-way ring is more efficient than crossbar of about 50%, thanks to lower wiring length and lower number of crossings. In terms of total power, instead, this effect is at 30%. This gap between 50 and 30% is mainly caused by the fact that in the total power is preponderant the contribution of receivers. In fact, notice that in the 8x8 for the crossbar, since it is characterized by higher insertion loss, the contribution of laser modulators is higher with respect to those of the 7-way ring. So finally, as you can see, ring topology is certainly an appealing solution for our target architecture. In conclusion, in this paper, we have argued design predictability concern in optical network on chip design that arises from the need to satisfy specific placement constraints. Processor memory communication in a 3D stacking approach is taken as a quantitative case study. Experimental results demonstrate that there is a large deviation between logic scheme and its physical implementation in terms of insertion loss as an effect of placement constraints. Ring topology is certainly an efficient solution followed by an optimized growth. Notice that these results are certainly strange because an abstract and pencil and paper consideration are certainly no good to predict the network quality metrics. And then an automatic placer route tool is a must to overcome this important gap. But even more important, to consider placement constraints and physical implementation trade-offs. In our future work, we would like to address scalability concerns for optical ring topology, making emphasis on the crossing concern at the initiator interfaces, and also the wiring length of a edge. Moreover, we would like to assess scalability properties of wavelength-routed optical NoC topology, targeting network partitioning and not global connectivity, and making emphasis on wavelength reuse. All in cooperation by the Technical University of Munich. In fact, right now we are working about to construct an automatic placer route tool flow for optical NoCs as a way to minimize, to bridge the gap in the field, contrasting optical network on chip versus electrical one. Thank you so much for attention.
Questions from audience?
Please.
Do you have any idea how
Sorry,
things would?
I cannot hear you.
Do you have any idea how things would scale up if you had 100 cores or 1,000
Yeah.
or whatever number you have?
Okay, in fact, it is our future work. But in our case, we evaluated real-life systems. So the number of cores is 64, okay? But in the future, probably, if you would like to satisfy these requirements, scalability properties, I mean, we talk about Corona or Firefly or CMP systems. One possible way, in my opinion, this is my personal feeling, and it could be to use network partitioning. Because if you use multiple networks, you can have different clusters. So if you increase number of cores in the underlying electronic layer, you can maintain stable the aggregation factor. You remember this slide? Very good question. It's so inspiring, this effect. Sorry, here. So if you maintain stable the aggregation factor, 16, and if you increase number of cores here, for instance, we talk about not Tilera 64, but Tilera 128 or so on. So we can maintain stable the aggregation factor, and we have a lot of clusters. But we can use different networks to satisfy this requirement. So in my opinion, the network partitioning, it could be a promising approach and suitable approach to satisfy network scalability properties.
Cool. Thanks.
Any more?
So it seems like things like the ring of rings is probably a good thing. Or
Okay, very good question. But this was discussed in another paper and date. So I discussed this result in the date 2015. So ring topology is good for global connectivity, but when you consider, for instance, scaled system like CMPs, for example, so ring suffers so when increased number of cores, the die becomes large, okay? And then increased propagation loss. Propagation loss here is not the most important features because it's the crossing loss, which is the preponderant in the insertion loss. So when you consider this kind of system very high, increase the propagation loss, and then the ring topology may become overly expensive. with respect to other topologies in a network partition way. So I hope the answer is good for you.
All right, so let's thank speaker again.